today's topic is range searching, which is probably one of the most important areas of computational geometry, and also applications extend to almost every area of computer science, namely, you know, database searching and more closely probably, geographical databases. Okay, so what is it? So there's a very general definition, but let me not get into too much generality, but just give you a reasonable definition of what it is. So you're given a set of points in, let's say, in a plane, more generally in d dimensions. Okay. So given a set this. We are allowed to build an appropriate data structure that supports query of the following kind. For some range, I just define what I mean by ranges. Some given range, just a moment. Range delta we should return. Okay, there are two kinds of queries. One is reporting query, where we must return all points in delta intersection S, or the cardinality, basically number of points. And what is a range? A range is a family, let's say predefined family, of subsets of the Euclidean d dimension. Right. Okay, so simplest case, or let's say very natural case, would be example points on plane okay, and my range could be, let us say, rectangle. So this is a natural query for database kind of problems. So your query range is a Cartesian product of two intervals, right? So you could specify that give me all the points that have x coordinates between x1 and x2, okay, and simultaneously between y coordinates between y1 and y2. Okay, so this is your Cartesian product of two one-dimensional intervals, and most common database queries can be posed in this way, that you have points in some dimensions which corresponds to the attributes of in some high dimensional spaces. If I have 10 attributes, then I will work in 10 dimensions. Okay, and then you have a query that give me all those points or data that have x1 coordinates between this and this, x2 coordinates between this and this, x3 coordinates between this and this. So, that will be a hyper rectangle. So, a general query. Okay. So, a general database query can be posed as a hyper rectangular range query. And the most trivial example of this thing would be one dimensional, right. So, I have points on a line, okay, and my intervals are closed intervals. Sorry, my ranges are closed intervals. So, either this or it could be this, etc. Now, the important one of the things that I have actually mentioned in the definition, but strictly speaking it need not be a part of the definition, is I am already referring to a data structure, okay, that build an appropriate data structure that supports the query of the following kind. And this is under the assumption that there is not one query that you want to handle, but a whole sequence or family of queries. If it were just one query, suppose we were interested in only one query. Suppose there would be only one query, right? Then clearly, the overheads of building a data structure, okay, is something that you do not want to bear. It is something that is not worth it. So, what you are going to do is what's the most trivial way of answering a range query. So, this range intersection S. So, I am going to basically determine for every point, okay, the trivial algorithm will be for every point. So, trivial approach for every point in the set S, determine if P belongs to the range, right. And assuming this is a simple constant time test, right, usually your ranges are not going to be too complicated. I mean, although I have not put any restriction in the definition, but mostly this test, okay, usually it is a constant time test. And if that is so, then for any kind of natural range query problem, you can provide the answer in order n time. Just check out every point with respect to that given range, whether or not it belongs to the range or not, right. So, order n trivial algorithm, and it does not really require you to build any databases, any data structures. But the problem becomes interesting once we go beyond this one query or a few queries things, that there could be a large number of queries, perhaps millions of queries, or it's just like a continuous process where you get these queries. So, for multiple queries it makes sense to build a data structure so that the overheads of construction is justified, and we can return the answers quickly. Quickly meaning not like order n time, something fast, hopefully something polylogarithmic, but there is a catch. But then we are used to this model now. So there are these two kinds of queries, right? That all points. So one is the reporting query. So this is the reporting query, where I am supposed to report or produce as an output all those points that lie in this range. The other one is a counting query. Okay. And by now you are used to the fact that in the reporting query the minimum time should be at least the size of the answer or the output. In the case of number of points, that becomes much simpler. It's some number between 1 and n. That's much simpler. But then in the type 1 kind of query, which is the usual kind of the more common kind of query, there would be some kind of additive thing. So it's not that ideally we would like to report it in time proportional to the number of points in the range, but then you do encounter some fixed term, and that fixed term is usually a polylogarithmic term. Okay. So ideal kind of bound for range query. Okay. So this quickly, so for reporting we mean, let us say, about order some polylog plus output size, and in the counting we would expect some polylog. So this is basically the objective when we build a data structure, right? And also almost equally important is the what's the other parameter? The size of the data structure, correct, right. Okay. The other thing is the size of the data structure. Okay. And somewhat less important is the pre-processing time. So with this in place, these definitions in place, let's see what we can do with this. Okay, I already drew this picture. So for points on a line, okay, and the ranges are intervals. Okay, let me shift to the other one. So the simplest case probably. Points on line and ranges are closed intervals. Okay, this is my given set of points, and at any point of time I could be given, okay, what is report all the points between x1 to x2, right? Or it could be any kind of interval, or this one, could be this one. So how would you solve this problem? Yeah, this looks rather simple. So you must basically locate your left boundary of the interval, okay, and if you have kept this point sorted, so essentially what you are doing is sorting the, so pre-processing is sort the points, right, and query answering is locate the left boundary using binary search, okay, and start walking basically, right, start reversing, and outputting until you reach the right boundary, right. So if it is this one, I locate this one in using a binary search, and then output this, output this, output this, then I find that I have reached the right boundary and that's the end of it. So, what is the query processing time here? Right. So, log n for the binary search plus the output size, right. So, that is your ideal bound of log n plus output size, sorting the points. Let us say if you use the comparison sort and log n, and your data structure size is nothing but a sorted list order n, right. So, all these figures are exactly what you want it to be. Right. So, okay, one dimensional problem usually are much simpler. So, time to graduate to the next dimension. Okay. So, there is maybe one more variation I should just mention. So, all is fine till now, but what happens if we also have this provision that points can be deleted or inserted? Exactly. Right. So, in the one dimensional case, so let me just write it here. Further variation or natural variation on these. So, range searching problem may have this following variation, which is very natural variation. One is the static case, okay. The other was is the dynamic case, where the underlying point set can change. And in the case of one dimension, even if the change, as someone suggested, instead of a sorted array or something, you just go and do your some favorite balanced tree structures, okay, which supports insertions and deletions, and that is it. So, all your bounds remain unchanged asymptotically. You still have order in space, you still have order log n plus output size query time, and in addition the other parameters are what is the time to insert and modify the data structure, right. So, moment you have this, then the additional parameters basically another important parameter is time to update the data structure. So, this one also should be ideally some polylog is what we should be aiming for. For each point inserted or deleted, I do not want to incur too much cost in modifying the underlying data structure. And in the case of one dimension, again this is order log n, right. Insert point, delete point, everything is order log n. So, in one dimension we have everything ideal, whatever we can hope for. Right. Does the same thing happen when we go to higher dimension? Okay, the higher once we move to higher dimension, that is 2 or more, there are actually two things that happen. One is, in the case of one dimension, what are the other kinds of ranges you can think of? I mean, the kind of ranges we dealt with are interval ranges, right, the subsets that are queries. And if you, I mean, I did not say it explicitly, but clearly the data structure that you have designed should depend on the kind of ranges you are supposed to handle, right. So, you built this data structure that whatever sorted set or a balanced tree, assuming that my query ranges are going to be intervals, closed intervals. And in one dimension, you can't really think of much variations from there, right. You can probably think of union of intervals and things like that, but they are not very natural kind of queries. Even if it is union of intervals, we know exactly how to merge them, etc. Those things we can handle rather easily. Okay. But the moment you go to higher dimensions, right. So, those Cantor sets and things like that are sort of way out of what people would like to query. I mean, the querying sets. See, here we are trying to specify. Yeah, those are implicit kind of queries. Here we are talking about explicit ranges, and I'm actually presenting the description of a range in some way explicitly. Okay, so in that context, there is not a whole lot of variation you can think of, or there is. I mean, natural problems are not going to sort of deviate much outside of that. What kind of, maybe you can think about open intervals or closed intervals, something like that. Maybe union of some finite number of intervals, perhaps, but not too much beyond that. Anything beyond that, just becomes, as someone said, it can be described mathematically, but probably not that useful in real life. But the moment you go to higher dimensions, okay, your ranges could take arbitrary shapes and forms, right? So the generalization of the interval range query would be the Cartesian product, right? So that's the rectangular range query. So one is that rectangular range query, and not only rectangular, but orthogonal, right? So it's basically Cartesian product of one-dimensional things. Okay. But then it can have any other kinds of shapes. So the rectangular range query need not be orthogonal. It may be aligned. Okay. So aligned rectangles. Okay. Other kind of natural queries are, circular range queries. And that's very natural. What is it? Basically, I am presenting a ball. Okay, there is a ball of radius r centered at some c. Okay. What are the points inside the ball? And that's something very natural. I am located somewhere, and I want to know exactly how many points occur within distance r from there. Okay. So that's your circular range query. If you want to handle arbitrary shapes, okay, well, at least if you keep it linear boundaries, then it could be a simple polygonal query, right? Okay, someone is interested for some reason to know how many points are inside this, there will be how many points are outside this, right? Now, this actually does not go well with our earlier model, where we are saying that we could test whether a point is inside or outside a range in constant time. I mean, if I give you a simple polygon, okay, to test whether a point is inside or outside a simple polygon, it may take you more than constant time. So what kind of, suppose it is a simple polygon and you want to test whether the point is inside or outside, and you are allowed to build a data structure, how quickly can you answer it? Constant time doesn't seem to be, because it's completely independent of the size of the polygon. That is an unnatural or an unlikely answer. So what is the minimum time you can think of? Yeah, so it's kind of a ray shooting query will help it. So if I could build a ray shooting data structure on a simple polygon, and that will be log n, okay, but it's not constant time. So it's, if it is not constant time, you may actually want to modify this polygonal range query in terms of, you may want to actually decompose the simple polygon into a union of triangles or something. Okay, so you can think about this polygon as I triangulate this polygon. Okay, and if I can actually answer a triangular range query, then I can just union these triangles and get the final answer, right. So the union of triangular range query will yield the answer. Okay. Again, there are some mathematical possibilities where this is a simple union, okay, and this is sometimes also where I'm going to only add up, okay. sometimes simple addition don't work, okay, depending on what kind of problem we are handling. So, here we are handling points and simple polygons or ranges. So, you can actually generalize the whole range query problems, not to be just points, but could be any kind of objects, okay. And then this simple kind of addition or unions is not going to work, okay. Then one there is a natural generalization which uses some kind of operator, okay, operator to combine the answers of these triangles, right. But I don't want to get into that right now. Let's not get into too much of generalization, and these operators are usually, so I'll just mention this, okay. And this perhaps little later in the course, I think Professor Agarwal will talk about what is called non-orthogonal range queries. So, we are going to mostly focus on orthogonal range queries. So, there are some ways by which you can combine the results of the individual triangles using some, usually these operators are called semigroup operators. And just to give you just one example, suppose even in the simple one dimensional case, okay, these points had some kind of it's not a single dimensional problem really, so these are points and they have some attributes maybe which is like some kind of height, okay. So, this is some height, this is some height, so on and so forth. Maybe it's some function, basically some discrete function, okay. And I give you a query where, yes, it's a interval query. Tell me the highest y axis in this interval. So, of course, in this interval there are only these points. So, that's the first job, is to find out which points are we talking about, which points are in consideration, okay. And after that I am going to do some kind of a max of the y coordinates of the points in the range. So, this max is an operator, okay. I am not, this is not a two dimensional problem where I am saying that these are these points and I give me all the points that occur within this rectangle. This problem and this problem, they are not the same, right. So, this is actually a one dimensional range query problem, okay, where there is an operator, underlying operator, which is the max operator, okay, and semigroup basically means associative operator. So, it's this operator will also act on the result of the range query, and that's how we'll get the final answer. So, this is also a range query problem, but it's a more complex range query problem, and you can really sort of build very complex range query problems from more and more general definitions. Right. Okay, so I'll just leave it at this, and let's proceed with the two dimensional case. Okay, that's the immediate problem at hand. The axis, yeah, parallel to the axis. Aligned would be, it may not be parallel. Yeah. Right.
But then why aligned? I thought alignment is aligned with the axis.
Well, I just called it that. So, I am calling it orthogonal, I am calling it aligned at any angle basically. Okay, so let's look at the two dimensional problem. And the first solution that we will examine in the two dimensional case actually comes from a very general principle. Okay. So, let me first talk about the general principle, okay, and then we will see that it kind of falls out immediately from the general principle. So, when you have these points, one way that we can do some pre-processing is kind of cluster these points. Okay. So, clustering is a very vague term. Okay. So, I deliberately want to keep it vague. Okay. In some way we are going to sort of partition or cluster these points. So, I am just drawing some arbitrary clusters. Right. Maybe this is one way. So, these clusters are not too bad in the sense that they are fairly sort of convex kind of regions, but it need not be. So, in some way we have grouped or clustered these points, right. And then my range, the range query, the kind of subsets that I am dealing with, let us say also has some kind of arbitrary shape. Perhaps it is a triangle. Let us say if a triangle is a very could be any, it can be aligned in any way. So, suppose here is my query range. This is my query. So, I have built a data structure where I have a description of these clusters. Okay. So, I have some description of these clusters, and usually again the description will be, let us say, some order 1 kind of description. These are like some, maybe some rectangular clusters or some circular clusters, whatever, some groupings which can be defined easily. It is not a very complicated shape which will require, which have a large descriptive complexity. So, they have some simple description, these sets of points, and then I am given this query triangle. So, one simple observation is the following, that okay, let me have another set of points here. So, let me make these observations rather simple, but will be quite useful later on. So, let us call this region 1, region 2, region 3, region 4, region 5, 6, region 7. So, what I can claim is the following, that we need not examine R7. Can you tell me why? Exactly. So, this region or the description of the region that I have, suppose I have a way to figure out, does this query triangle intersect with R7? I am not asking individually all the points, I am asking the question about R7 and not the points inside R7, right. So, R7 can contain many points. I could simply ask, is any of the points in R7 contained in this query triangle, okay, and I can test them individually, but I do not have to. I can simply find out, because this R7, this entire region R7 does not intersect with the query triangle, I can conclude that I did not look any further, right, because R7 intersection the range is empty. So, there can be many such regions. R6 also is another such region that it does not have any intersection with the query triangle. The second kind, of course, is the other direction, right. All points in R3 should be reported. Why? It is completely, it lies inside this range, right, because R3 intersection this is R3. Okay. So, these are the two extreme cases, and what can you say about the rest? We really do not know. I mean, the query triangle intersects R1, R2, R5 and R4, okay, but I have no idea how many points inside R4 or R2 or R1, because I only know about the description of this region. I do not know how the points are distributed inside. I have not kept track of that, or it is very difficult to. Okay. So, based on this information, I have to look further or examine how many points in R1 and R5 and R2 and R4 are contained inside the query triangle. Okay. For the remaining, we need to examine further. Whatever it means. Okay. And whatever it means, what is the natural way of sort of doing this, taking it further? Right. So, again R1 is a set of points, R2 is a set of points, and I am going to again do the same thing within these regions, right. So, maybe I will just have some more clusters here, okay, and so on. So, now I am going to, my final answer is going to be the union of the range query of this triangle with R1, again R2, R5 and R4. Okay. So, I have branched out now, right. Unfortunately, now this whole thing, suppose I call this entire thing the set of points as R. Okay. So, R, the range query to R is the regions that completely lie inside, that is taken care of at the first level itself. The regions that do not intersect, that is also taken care of, but recursively we need to handle all the regions that partially have some partial overlap with this, right. So, it becomes union of R1, in this particular case R1, R2, R5 and R4, which actually is not good news, right, because if you want to write any kind of recurrence relation for the query time or whatever, then from a single point you could have, a 4-way branching and things like that. And if you have 4-way branching or 5-way branching, who knows, the whole thing is may not turn out to be very efficient. After all, what do we want? Our goal is to report in time proportional to a fixed logarithmic term or a polylogarithmic term plus the number of output points. But any kind of recurrence where you have so many branches is unlikely to be very efficient. Right? So, that is why we have to be careful when we define this partition. Right? So, this is a very general approach to range query, that given the set of points we would like to partition them in a certain way, and then the query will be answered as union of which partitions this query triangle or whatever the query is, the range has non-trivial intersection with. If it fully overlaps, no problems. It does not overlap at all, no problems. But partial overlaps are the ones which have to be recursively sort of handled. Right. So, we will basically in 2 dimension we will look at a special way of defining this partition. So, this is a very arbitrary partitioning at this point, okay, and that's where I could have a 4-way, 5-way, who knows how many ways I have to recursively look for. So, I want to somehow bound the number of branches that I am going to have. So, any suggestions or any ideas? How should we branch or how should we partition these points? And we are handling orthogonal range queries, okay. These are not arbitrarily aligned rectangles. You know the solution, okay, fine. So, thanks for confessing, but if no one else answers, I will let you answer. Yeah, it would be some kind of binary search. Binary search is a very, what should I say, ubiquitous term, so there are many ways that you can do binary search. Okay. So, what are we partitioning on then? Half-half. In what direction? Half-half is a good idea. Half-half basically means that your data structure, the depth of the data structure is going to be sort of logarithmic, right? Half-half. Half-half is a good thing. Yeah. So, how would you partition those points? Yeah, hierarchically fine, but that's what we said. We already discussed that we are going to recursively partition further. But let us say at the top level, how are you going to partition? We are handling only rectangle range queries, huh? What's query triangle? No, I am not handling query triangles. Although I gave the example as a triangle because it works for any kind of ranges, but we are going to looking at only for schemes for rectangular range query, orthogonal range query. Okay, take the median along y or x. Okay, doesn't matter. Okay, let's take x first. Okay. So we have I had an example. Is this visible? Can't? No? Okay, I will draw it then. But the basic idea is clear, right? So, I am going to okay. That's visible? Let's see, let's put it like this. Is it visible now? Better? There's a glare. Okay, fine. I'll do it. I'm just being lazy, so I'll do it now. Not that I need this exact point set, but it was just. P15, P16. So, there are 16 points here. Okay. So, as all of you agree, we should try to find a median. There are 16 points. So, well, the numbering of the points was such that it was like this. So, I partition. So, my first level of partitioning is this. I draw the median along the x coordinates. Okay, what should be my next this thing? Okay, so someone already is saying, let us not be partial towards one coordinate. Okay, let's also treat the other coordinate fairly. So, this is x coordinate. Now, how should we partition it? Should we just draw? There are a couple of ways. So, I have these 16 points, and I could actually draw a y, so that I balance out the number of points above and below. Do you want to do it that way? That's one option. What's the other option? Yeah. So, I treat these separately. Okay. So, this set of points and these set of points will be treated separately, because this is one partition, is another partition. Now, I recursively partition this and recursively partition this, but then now I use the y to partition, the median of the y to partition, but then they are handled separately. So, there are 8 points here. So, on the left side, 1, 2, 3, well, I do not know which one, 4, okay, maybe this one. So, this looks like a separator in the y direction for the left sub problem, and for the right sub problem, maybe this one. Okay. So, you can see that these two lines, they are not the same lines, so they are not flush, they are not necessarily flush, because we actually partitioned them separately. Right. Now, what do we do after this? Okay. Now, we treat. So, now I have this one set of points, second set of points, third set of points, fourth set of points, and we are back to the original problem. And again, within this each of this partition, I can do the the x y partitioning again. I basically recurse like this. Okay. So, that is what I do. What happens when I get a query rectangle? Right. So, when I get a query rectangle, well, I could be lucky and I could get a rectangle like this, which means that. So, how is the search tree built? Okay, let's first look at that. How is the search tree built? The search tree is built initially, there should be some node of the tree that corresponds to the entire space, the entire point set. Okay, so, this corresponds to the entire point set. Then we partitioned along the x axis. Okay. So, I create two nodes, okay, corresponding to the left half and the right half. Okay. So, this represents the left half of the point, this represents the right half of the points. Then within each of these halves, left and right half, I have the up and down. right. So, this is again the up down and up down, okay. And at this point we are basically back to the original problem, that again we can repeat the same thing. So, in 2 levels, after 2 levels, basically again we do the left right up down, left right up down. So, alternately we do the x and y axis, right. And eventually when we have only one point, we do not need to do anything, right. Every time we are partitioning, or we branch to a left right child, now we are reducing the number of points, and this process can't continue for too long, because every time we are halving the number of points, the depth of this tree is only logarithmic, okay. And finally each leaf node is going to be associated with only one point, okay. Now what do we do for these intermediate nodes? That we will see later. Whether we are going to store all the points here or we do not need to, that is something we will find out later, okay. But what we need to certainly do is that with each of these nodes we need to store the description of the region associated with that. So, the initial node must, we can enclose all the points in a rectangle, huge rectangle. So, it will contain the description of that rectangle. This and this will contain the description of the left half, the left rectangle and the right rectangle, which is a constant time description, constant size description, okay. So, each node is associated with some rectangular region, okay. And because we have actually made we have enclosed everything in the box, every node will basically be a bounded rectangular region, right. So, every node of this tree, every node corresponds to a rectangular region, and that what makes life easy for us, that any time we get a rectangular range query, I can quickly find out whether or not it has any partial overlap, no overlap or complete overlap, because these are all, my rectangle also constant description, my nodes are also constant description. So, I can quickly determine whether it is a full overlap, partial overlap or no overlap. So, I can make that those tests are constant time tests, right. Eventually in the leaf node we will have these points stored, okay. We will see whether or not we need to also store these points in nodes, may or may not, depends on what the algorithm is going to be like. At this point we get a rectangle, okay. So, I compare the rectangle with the region of the left, well it does not overlap. So, I do not need to proceed along this at all, okay. So, this rectangle does not proceed along this at all, it completely lies to the right of the median line. So, the search path it takes is here. Next level, unfortunately we are not so lucky, because it intersects both the up and down, okay. So, we need to, the search path is like this, and then it actually branches to both sides, gone. So, maybe you have lost all the advantage, because what happens if we keep branching on both sides, okay, eventually you know that at the leaf level we will have to deal with about order n nodes, okay. Order n, so at every internal node we need to do a constant time check, right, whether it has partial overlap, full overlap or no overlap, right. Now, if this kind of branching continues, let us say up to all the levels, almost all the levels, then what do you have? Suppose it is branching all the way up to the leaf level minus 1, then what happens? Every time it is a branch of 2. So, every time it is 2 times 2, let us say about log n minus 2 times, how much is this? Yeah, it is almost n by 4, okay, which means that we have lost whatever we are aiming for in terms of saving query time, it does not, gone. Well, these are claims that you are making, I am not convinced about it. We will have to analyze it. What I am saying is, well, I mean interval trees are interval trees, okay, this is not an interval tree. This is by the way called a range search tree, okay. It is a range search tree, and it is a very special kind of a range search tree, which is called, in the literature is called as a KD tree. Why is it called a KD tree? The D stands for dimension and the K stands for the number of dimensions, okay. So, in this particular case what I have drawn is essentially a 2D tree. In k dimensions you are going to cycle through these coordinates. So, all the k coordinates. So, here we cycle through first partition along x and then y. when you have these k coordinates, then you are going to cycle through all the k coordinates, then go back to the original problem. Okay. Again, partition along the first coordinate, the second coordinate, all the k coordinates. Right. So, it is called the KD tree in general. It is a very common and powerful data structure, okay. But this is the basis of it essentially, that you are partitioning the points. You have a range, and it is going to you are going to build a search tree based on that, and you are going to fork or follow certain search paths depending on which of these nodes this rectangle intersects with. Okay. So, the real question here to analyze is, of course, what is the space. Each node occupies only constant space because the region description is constant. Okay. But depending on whether or not I store the points also, I do not know. If I store the points also, then at every level I will store a point, then it will be n log n. So, I would say maximum n log n, depending on what kind of storage scheme we use, but then it may also be order n, if you are lucky. So, with that we will have to figure out. Okay. This is a space. More challenging is the query time. And what is the query time really? The query time is the number of internal nodes visited by the search, the recursive search. That is precisely the time of query. And finally, when you reach the leaf nodes, we just either report the point or do not report the point. So, in terms of the output size, it is either going to report or not report. So, you are going to charge one for the reporting and not charge for the not reporting. So, the plus output size kind of falls immediately from here, but number of nodes visited is the fixed term. So, how large is this term? What is your guess? Tell me. First, we will look see if you can guess it, and then we will try to, if we have guessed it correctly, we will try to analyze it. Log. 2 log n. Wow. Okay. Any more guesses? More complicated functions, less complicated functions? No one thinks it is constant. Good. Okay. Because at least the search path will be taking at least one path, right? So, that is minimum of log n. Anyone willing to guess log star n? No, log star n is too small. Okay. So, 2 to the power log star n? No. So, since we are running out of time, what I will do is I will give you the answer, let you think about it overnight, and tomorrow I will complete the proof. Okay. Some of you should know, because you have done some course with me where I think I may have discussed this. Okay. Okay, last chance. Log 3 by 2. Still stuck with logs. N, yeah, n is certainly an upper bound for sure. It cannot visit more than n nodes. N log, no, n log n is way over. You will be penalized for that answer. Yeah, I heard it. I heard it. Yes, root n. Got it. So, you may think that root n is, I mean, the reason maybe you did not try to guess root n is because it is not consistent with our goals of polylog. Okay. But there is a catch that I will explain tomorrow. So, it turns out that the space is order n, that I do not need to store points in any of the intermediate nodes, okay, and I will be able to analyze where I will show that the number of nodes visited is no more than square root of n, okay, by any rectangle, any rectangular range, and this is almost the best possible. Okay, that is the surprising part. The surprising part is, surprising news is that if we use order n space, query time, one can show a lower bound of square root of n. This is a very rather unexpected result actually, and it's very difficult to prove. Will not attempt to prove it, but this is known. So, if we restrict ourselves to linear space, okay, we are bound to encounter in the worst cases about square root of n. Right? All right.